Perfect. Okay, thank you. Well, so I'll reiterate what Brian said and thank you guys for inviting us to your party. Where, me specifically, I come from a neutral atom, neutral molecule world. And so, you know, being here is really a treat. I feel like I'm learning a lot, and I really appreciate being included. So what I want to tell you about today is a project we're having some fun with at UCLA where we're sympathetically cooling molecules with laser-cooled atoms, and an outline is shown here. I'll start by just very briefly, I'll do this in just one slide, tell you why you might want to work with molecules. As Brian said, it's actually really hard, and so it should be worth it, and so it's okay to hear it twice. And I'll do that with what I call the big four, which are really the 4 reasons we're doing this. But if you understand molecular rotation, and after this talk you probably do, or the previous talk you probably do, that's the key, that the rotational degree of freedom is somehow special, right? It's this beautiful quantum system where you have strong transitions, you can address 2 levels at a time. And so it's the thing that, in one way or other, all 4 of these things come back to that fact. So then what I'll do is I'll suggest to you that sympathetic cooling might be an elegant way of making molecules cold from a large class of molecules. But what we'll see is that there are a couple of problems you run into pretty quickly. And I'll argue that if you're willing to work with charged molecules, there's a solution to those problems. And then normally when I give this talk, I then go on to say, hey, molecular ions are still molecules. They still rotate. You can do all the things you want. But I think in a community of ion trappers, I'll just skip that. And then what I'll do instead is go straight to the meat of the talk, which is to tell you about the hybrid atom-ion system that we've been working with, which we call the motion trap, and you'll see why. And here I'll give you, I guess I'd have to call it a revisionist history of what happened. Because if I tell it to you in the way it should have happened, it'll make more sense than if I tell you the way it actually happened. And I'll start by first showing you some work about motional cooling, which honestly you could trace back all the way to day melt, some of the things we're dealing with here. And then I'll segue and end with some very recent results that we're excited about, where we see now some evidence for internal state cooling of the molecules. All right. But before I do that, let me do my acknowledgments for the people that actually did all the work. Wade Religer was a postdoc turned research professor who finally got lured away to JPL, who had his hand in basically everything that I'm going to talk about. Scott Sullivan did his PhD on this experiment and also had his hand in most of the things I'll show you about. Kwong was involved in the early spectroscopy I'll talk about, but more recently, about the last year or so, year and a half, he's been working on understanding collisions in these ion traps, and it's really catapulted, at least my understanding forward by quite a bit. Stephen worked on the spectroscopy, took it a little bit further. He also developed this nice mass spectrometer we use, and now with Christian, the new postdoc from Tobias Schatz's group, he's implementing the 2nd version of the experiment. And of course, everything is centered on Svetlana, who without her help would be lost. And I'll also acknowledge my recent colleague at UCLA. So Wes came about, some of you may know Wes, he came about a year ago, and what had to be record time, something like 8 months, had trapped ions and ultra-cold atoms. And having him around has been a real boon for our effort. All right, so the big 4, what are the big 4? And I'll go through this quickly, because so there are proposals for quantum computation with polar molecules. And again, there's many different ones, but the idea is rotation is this beautiful quantum system, right? It's long-lived. You can address it easily. You can use that to store your quantum information, and then you can use the dipoles of the molecules to enable your quantum gates, right? So it looks fast, it looks scalable, it looks great if you happen to have a bunch of ultra-cold molecules laying around, right? Fundamental physics, precision measurement. Here the story is very simple. Molecules are just more complicated, right? They have this extra internal structure, so there's more chances for accidental degeneracies and enhancements. And you know, this is already being used in things like the thorium oxide electric dipole moment, measurement, which you guys all know about. Then there are a lot of proposals for people like Peter Zoller, Peter Robel, of doing simulation of, say, condensed matter systems or other things with molecules. And this is a specific example where they're considering polar molecules in a lattice, and here letting the interactions simulate quantum magnetism, right? And then there's one that really, you could argue, is a whole field into itself, and that's quantum chemistry. And in my mind, this is at least what I think the ultimate aim of chemistry ought to be. And that's to prepare molecules that you're going to let react in known quantum states, both motional and internal, direct them through the reaction, or at least to just let the reaction proceed, and then know with quantum state specific precision what the outcomes are, right? I think this is how, if you're ever going to get to the point of really controlling chemistry, you do it. All right, so that's the motivation that all of us that have been working in the molecule field for a while are after. Now, if you know this field, you know it's been going on for almost 15 years now, right? And the challenge we're still facing is how do you make these molecules cold, right? These extra internal degrees of freedom that make them more interesting also make them a little bit more ornery to work with, right? So when we started our work at UCLA, we sort of took a step back from the problem and said, okay, we know about all these techniques. We've used a lot of them, photodissociation, magnetoassociation, Zeeman deceleration, Stark deceleration. But is there a simpler way that might be more general? And what you realize is that helium cryogenics is a great thing, right? You couldn't put a price tag on all the science and technology it's enabled. You know how to make helium cold, and so you can just basically cool down anything else. Unfortunately for us, that's not quite ultra cold, right? And so we asked the question: could you conceive doing ultra cold atom cryogenics, right? You know how to make laser cooled things, so why not use that to cool things down? Well, obviously that's not a particularly novel idea, so there must be a reason people don't do it. And there are several, but the two main ones I'll talk about now. The first one is what I call the cocktail problem, and I'll illustrate it with Chris Monroe's favorite form of sympathetic cooling. It's a little bit cutesy, but it really is one-to-one, so just bear with me. Right, so if you had a long day at a conference and you want a cold drink afterwards, there are three things you have to have, right? There's your whiskey, there's the ice cubes, and then there's your glass. Well, when you try to make your cold molecule cocktail, it's one-to-one, right? The molecules are obviously the whiskey, right? That's the thing you want to cool down. Your ice cubes, we'd like to use laser-cooled atoms, right? This is what we're after. And then that's where you hit a roadblock, right? So in the neutral molecule world, where I come from, this is fundamentally the problem that the whole field has been facing for the last 10 or 15 years. And it's the fact that with lasers or static or even electromagnetic fields, the best you can do is of order about 10 millikelvin type of potential, right? Now, okay, if you use superconductors, you can get a little bit higher. But so now you have this perverse situation where I want to make this thing cold, but to make it cold, I need to hold on to it. But I can't hold on to it until it's cold, right? And so fundamentally, this has been the problem. Now, if you're willing to work with charged molecules, right, this is a trivial problem for you. I can just work with a molecular ion, put it in an ion trap, and now I have my glass, right? So even if it's 1,000 Kelvin, I can trap it, right? And then I have time to cool it down. All right, so let's charge molecules to the rescue for problem one. But there's another problem. And I call this problem the vibrational problem. And the best example I know of it comes from John Doyle's work here at Harvard. And this is an experiment he actually did with Wes, who's my colleague now, where they had NH molecules trapped inside of a superconducting magnet, and then they had helium buffer gas in here to cool it down. And they see it quickly cools down the motion and the rotation, but they saw that it never touched the vibrational degree of freedom, right? And if you want to think about that in a simple way, it's basically, you have a vibrational degree of freedom, which is the molecule doing this, right? Now the speed of that is much faster than the speed of the collision. So while this thing is doing this, this guy kind of comes in and then he goes out, and there's no energy transfer, right? So this was so slow they couldn't measure it. They just put a limit on it of less than 10 to the minus 15 cubic centimeters per second. And so instead what they did was measure the spontaneous emission lifetime of these vibrational states that was so long-lived. Right? Now you might argue, well, this still happens. I went to my thermodynamics class. I know that eventually you reach equilibrium. But the problem's a little worse than that, right? If you want to do sort of ultra-cold atom cryogenics, you don't have this nice chamber wall that's at the same temperature as your atoms, right? So you now have two competing reservoirs. You have your molecules trying to cool things down, but you have the black body of your chamber heating it up. And blackbody can be significant. Right? So you actually have to outrun blackbody. Right? So what we argued in 2009 when we started was that, well, because of this 1 over r to the 4 potential, we basically did some semi-classical hand waving and said that you should get near unit relaxation efficiency of the vibrational degree of freedom. And again, I mean, I'm letting the cat out of the bag a little bit, but the point is that because you have this 1 over r to the 4, if you want to think classically, this collision speed is better matched to the vibrational motion. Right? And we'll come back to this later. All right, so those are the 2 problems you encounter when you start thinking about this, quote unquote, ultra cold atom cryogenics. And we argue that charged molecules solve it. So how do you do it? What does the experiment look like? It's pretty simple. We just take a magneto-optical trap. We use calcium, which might seem like an odd choice, but as you'll see as we go through the talk, you want a buffer gas that's very light. This was previously known. And you also want something that's not going to react with your molecular ion. Right? So if you think about an ion, they typically wouldn't mind having an electron. And if you think about something in the first column of the periodic table, they're kind of happy looking like a noble gas. And so when those 2 things hit each other, the ion steals the electron and the game's over. So we move to the second column where you get higher ionization potentials. And the lightest atom we felt comfortable working on was calcium. So ultimately, something like a beryllium mott, as odd as that sounds, would be the ultimate for this sort of game. It's such a high ionization potential that you could even do biomolecules, I think. All right, so we have a calcium magneto-optical trap, and then we have an ion trap. We do what Reese's did. We stick them together. And you'll see when you do this, watch. It spells the word motion, so we just call it the motion trap. You said as we go through. Well, it was a match made in heaven. All right, so what does this thing do? Well, we were thinking about it in terms of making cold molecules, but really it's a lot richer than that. When you have ultra-cold atoms and ions in proximity, there's possibilities for quantum chemistry, studying this atom-ion interaction, which surprisingly enough, this 1 over r to the 4 potential has not been all that studied experimentally at these temperatures. And then there are also proposals for quantum information. But the thing in parentheses is what's great for us, right? These are more or less proven technologies, right? They're maybe not quite turnkey, but they're pretty close. So what that means is you can spend a lot of time thinking about the science and less time, trying to keep your start accelerator running, which I know about. All right. So, and what's great about this as well is people like Mikhail Drusin have shown, all these beautiful techniques, and also all of you, that we haven't had in sort of the neutral molecule world before, right? You can make these giant crystals, but yet you can still see all the particles. You can even work with one. And so it's a whole new set of tools that we can bring to bear on these problems that we haven't had before. All right, and then I should say, but I guess you just heard it talk about it, this isn't the only way to do it. Drusin and Schiller have shown, cooling with atomic ions plus rotational state optical pumping gets you into the ground state, and as we just heard, Brian Odom has joined those ranks with a very exciting technique. All right, so here's our first implementation. So we didn't jump straight to working with molecular ions because I'd never even trapped anything in an ion trap before. So we started with our calcium mott, and we decided to use ytterbium. And we chose ytterbium because it has the same mass to charge ratio as the molecular ion we wanted to use. And so the idea would be it'd be a perfect sort of kinematic stand-in. And by doing this, we could laser cool it, take pictures, make sure the thing turned on, and et cetera. And we got all that. We also got some atom-ion chemistry that we didn't quite expect, and it turned out to be a lot richer than we had imagined. But I won't talk about today. There's some references here, and then also Dinshlag, Cole, and Willich have done very impressive work in this regard as well. But what we did instead of talking about this, what I want to talk about is the cooling, because even though this isn't a molecular ion, it should still be cooled by this calcium mott, right? If we just load some ytterbium ions in, do they get cooled down? Now, the great thing about ytterbium is that you have a simple level structure, so you can scatter photons. And if you do it, you can write and do some sort of quick scan. You can get a rough idea of what the temperature is very easily, right? And so we did this, and here's what you see. This isn't any special data. I just it happened to be on my laptop. So here's an experiment where we just load a bunch. So we're working with large ion clouds typically. We load a bunch of ytterbium in, no mod on, and we scan the laser. And you see something about 800 Kelvin, right? And so we understand why that's 800 Kelvin. We'll talk about that in a minute. Then you turn on the MOT, and you see that you cool it down to a blistering 600 Kelvin, right? You do have cooling, but to steal a phrase from John Bone, it's not sympathetic cooling. It's simply pathetic cooling. And so if you think about this, right, from a thermodynamic standpoint, like I have a reservoir at a millikelvin, it's not getting there. There must be another heat load, right? Now, that wasn't completely unexpected. We knew a little bit about this phenomenon, which we've taken to call micromotion interruption. Different people, I think, have called it different things. And I'll talk about it in the next few slides, but fundamentally what it is the atoms and the ions can mess with each other, and then they can bring energy in from the RF field and heat things up, right? All right. So I want to apologize to John Bollinger and the other people who know this, because this will seem incredibly elementary to them, but I'm new to this field. So I want to give you this simple interpretation of this micromotion interruption heating. And I'm going to illustrate it with what I call stopping collisions. So let's first consider just a ball rolling in a bowl. So this is a normal harmonic oscillator, no micromotion, right? This thing oscillates with sines and cosines, right? Now let's consider that it's rolling up the hill right here, and at this moment there's a collision with the background gas that stops it, right? So V equals 0. What happens? Well, from that point on, it just goes forward with some cosine oscillation where the cosine has a t equals 0 at the collision time. The amplitude is reduced, and it's a cooling collision, right? And it's always a cooling collision, right? So this is John Doyle's work. This describes the cooling in those experiments. Now, ions move with these Matthew trajectories, which are smarter than sines and cosines, right? A Matthew trajectory has a stopwatch, and it knows about the RF phase. And if you mess with it at the wrong time, it makes you pay, right? And let me illustrate that here. So here's a low Q Matthew trajectory. It looks pretty similar. Here's the micromotion. You have a collision that's a stopping collision now. So V equal to 0. Most of the time you get cooling, right? And the thing goes off with less energy. But if you happen to have that collision at the wrong time, and that wrong time is like when the micromotion velocity is very fast, right? And you force this thing to be stopped. What the ion says is, that's fine. I'm happy to have a V equals 0 total velocity, but my micromotion velocity is very fast. So that means I have a very high oppositely directed secular velocity, right? And the thing goes off with more energy, right? Now, if you're worried about energy conservation, it just comes in from the RF field, right? There's like 10 different ways of saying that, but that's the one I like best. All right. So what's happened in the last 6 to 12 months is my student Kwong has really tackled this problem from an analytical point of view. And our goal is always to have sort of simple expressions that I can understand, which this is pretty much at the limit of what I can do. This is actually a few more terms than I care for. But we can now do things that predict the steady state properties and the dynamics of this molecule or these atoms as they're being cooled by these ions as they're being cooled by the atoms. Right, so we can I'm not going to go into detail of how you get here, but I don't even want you to look at these equations. I'm just going to point to them. We can write down things like this, which are the ultimate temperature that you get divided by the temperature of your buffer gas. And it depends on things like the masses and the trap parameters. And you see over here so this is radial and this is axial, that these things, the dots are this Monte Carlo simulation. And you see that the analytical theory agrees quite well with it, right? And so you see stuff that's already been known that, as you crank up the buffer gas mass, you start to not cool as well. And eventually there's some mass where no matter what the temperature is, you get heating, right? And you can think about this in a hand-wavy way is, well, if I collide with something really heavy, I'm usually going in the other direction. Right? And so now I'm sort of maximally out of phase with the RF, and I get work done on me, and I get heated up. Right? So we can write down expressions for this critical mass. And so the dots are simulation, the blue's the theory. And what I should say is, this is following in the footsteps of a lot of people who've looked at this problem. John, all the way back to Damelt, DeVoe, Vladen has looked at this. There's a guy that gets overlooked a lot, Moriwaki, from about 10 years ago, who, in my opinion, I don't know, reading his work was the one that really helped us break through to understanding this. And so you can see now, though, that Kwong has really gotten it right. So here's Kwong's result. Here's the sort of Damelt result. Here's the DeVoe result. And then the Moriwaki result gets the shape right, but not the values. Right? In addition to steady states, we can also now talk about the dynamics. It turns out there are 3 different relaxation rates. It's sort of technical as to why. But the slowest one, which is in blue here, this is the relaxation rate as a function of mass, is the one that sets the dynamics for your experiment. And what you see is, well, as you increase the mass, and here's just some expression for it, initially the relaxation rate goes up. This is increasing the buffer gas mass, which is the tip, what you'd expect is as the masses get closer to being equal, you have more momentum transfer. But as you get too high, this heating effect turns it over, and eventually you end up in a range where you're always heating. Right, and you can see that the rates really do work out. So the rules of thumb of this aren't any different than what Damelt and everybody else knew. Is that you want a low buffer gas mass, you want a low Matthew Q, but now we can be a little more quantitative about it, and so we can set some fundamental limits on what we can do. And so if you're working with, say, rubidium as your buffer gas, then you really can't work with anything lighter than about 65 AMU, which isn't that restrictive. If you happen to work with calcium, you can go a little bit farther down, right? And so if you could work with beryllium, then you can access a larger range as well. All right. So we understand this, but it turns out that's not the dominant heat load. That's not what's causing the problems in these ion traps. This just sets what you can ultimately get to. The biggest heat load comes from the ion-ion interaction, right? So as these ions are swarming around in here, they're perturbing each other's Matthew trajectory, right? And if you don't have a Matthew trajectory, then energy can come into or out of you from the RF field, right? And so using the same sort of theory that led to those previous results, you can write down this equation, which don't worry about the details. It's just the heating rate due to the ions interacting with one another. So you have things in here like the density and the temperature. If there's any excess micromotion, that hurts you. But then we have one term you may not have seen before, and it's called log lambda, or if you're a plasma physicist, they call it the Coulomb logarithm. Now, so what is this funny thing? Well, it comes about because when you're writing this down, at one point you're doing an integral of 1 over the impact parameter, right? And so that blows up on both ends. And so Landau was the first to look at this. He said, well, okay, that's not so bad. I know at some long range there's some Debye length where you just can stop integrating. And on the short range, look, there's a distance of closest approach, right? E squared over r equals kt. That's called the Landau length. And if you integrate this up, you just get the logarithm of lambda d over rc, right? And away you go. Now, the plasma community has sort of a cottage industry of trying to determine what this function really is. I mean, lambda d over rc is sort of right, but you run into problems because in a strongly coupled plasma, it can turn out to where rc is bigger than lambda d, right? And so these ideas of how you even define these things break down. But the sort of first and what's been accepted for a while was after Landau, Spitzer, and some others picked this up, and they said, well, lambda d over rc was close, but if you use about 3/4 of that, it's better. Plasma physicists would never call this lambda d over rc. They use 1 over g. G for them is basically our gamma. So, we have potential to kinetic energy. They're not quite the same, but they're related. If you know one, you know the other. But in 2008, and what was a pretty big result, Guy Diamante and Jerome Dalaga at Los Alamos used the giant supercomputers there for simulating, nuclear type things, to simulate a plasma, and from that they extracted a expression for log lambda that works at high G, or higher G. And you see that, if you expand this at low G, you get this. So this was a big result in 2008. So we looked at this, and it turns out that because we're not really theorists and not all that smart, this form of this equation, you can't quite just plug this thing in. We expect it to work at low G. So at low G, if you just plug this into here, it works fine. But as you start to go to strongly interacting ions in an ion trap, there are things about that means you can't use this. So what we said was, well, we know everything here, so let's just turn this around and measure it. And so when you do that, this is what we get. So this is G, this is log lambda. If you prefer gamma, it's up here. These are sort of the gas, liquid, and solid phases, roughly defined. And what you see is this log lambda starts off at around, something like 10. And as you go to a more coupled plasma, it just decreases, right? And we didn't really want to think about it too hard, so we just fit something piecewise to it. And you can even make some sort of hand-wavy argument as to why here it should go as G squared, so we just use that. But, you could fit other things to this, right? And so the physics that's encapsulated here is sort of the physics you guys already know. And that is, when you're in these sort of solid or liquid phases, this thing's very small. So that means the ions aren't heating each other very much. This is why when you make a crystal, it can live in the dark for a while, right? So the way to think about it is the ion motion is very correlated, right? The excitations are phonons or even waves if you're in the liquid. And so the ions aren't getting out of phase with each other. They aren't whacking each other and bringing energy in from the RF field. As you move to the gas phase, that effect turns off. So what's this useful for? Well, for us, it's really important for understanding what cooling is going to be like in the motion trap. But I thought I'd just throw this up because it might be of interest to some of you. Here's an experiment where we had, I think this was something, it was 1,000 ions or something. I actually don't remember the number. And we cooled it down to 100 millikelvin or something. We turn off the laser cooling and just watch the thing heat up, right? And so in the beginning, and this is just heating up due to the ions, messing with each other. In the beginning, there's a very small heating rate, which you can't really tell because this is a log-log graph. But then there's this sudden, an abrupt melting of this thing, right? There's a huge heating, and then it's followed by slower heating. And so what we understand with log lambda is, look, here you're in the solid and sort of liquid phase, you're slowly heating. But eventually one of these guys kind of boils off enough that he can come in and whack everybody. And then everything falls apart. But then as it gets into the gas phase, the density goes down and these guys start heating each other less. And so this tapers off, and this will just drive you up till evaporative losses balance you at, sort of whatever it is, trap depth over 10 or something, right? So we can also, and so this is experimental data, and the red line is just an integration of that formula from before, right? So this takes like a couple seconds, whereas to simulate this took us a couple weeks, And you can get the density, the heating rate, blah, 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 everything you want. And you can sort of, in my mind, if I have an equation, I can think about how to optimize it a little better. One thing that might be interesting to you is you can actually write down an approximate expression for this time of this, I don't know, we've been calling it the melting time, but you could argue about what that is, if it's melting or boiling. And, it's not too complicated. But the bottom line is for sort of the smaller ion crystals, which people are using for quantum simulation and other things, this is of order 1,000 seconds or maybe a little more. But as you start to go to more and more ions, or you start to use zigzag structures, you bring in, either more excess micromotion energy, this number can come down. And so ultimately, this will be a fundamental limit to a quantum simulation or a quantum gate that you have to do in the dark, because eventually this thing can heat itself up. I mean, I don't think it's anything to worry about now, but maybe someday. All right, so the bottom line of all this is that in the current motion trap, we can't significantly cool the translational motion. But that's okay. We sort of had a solution in our back pocket all along, which was, well, let's just do a two-stage sympathetic cooling. So Drusen has shown us the way that, look, we can laser cool some atomic ions and cool down the molecular ions very quickly. And then we can use our MOT to try to relax the internal degrees of freedom, right? And so that's what we did. All right, and that experiment looks something like this. So we use barium chloride. I didn't really talk about why. There's some barium that we laser cool, and then we have a calcium MOT. All right, so you ask yourself, well, does it work? The translational cooling is easy, of course. And the real question is, what about the internal states? Are they being relaxed at all? And now you would say, well, how would I do that? Just as Brian was talking about, you want to use spectroscopy, right? You'd like to see some forest of lines, and that, if you cool it down, your row vibrational spectra collapses into just a few, and you can infer your internal population. Now, if you know about molecular ions, you know you've hit a problem, because there really isn't any spectroscopy for molecular ions. There's a few, but not many. In fact, when we started this project, this is all we knew about barium chloride. There was this obscure estimate of the dissociation energy at 38,000 wave numbers. And we knew just that it had to dissociate to barium ion and a chlorine atom just from the asymptote. So we got a dye laser, cranked it to 38,001, and tried to see if we could blast this thing apart. Right? And when it didn't work, we just turned up the wavelength, or turned down the wavelength and kept going. Right? And to do that, my student Stephen built this device, which has actually been pretty useful for us. He integrated an ion trap with a mass spectrometer where we can get radial ejection out of the ion trap, and when we really push on it, we can get almost isotopic resolution in about like this much space. And it lets us work with a lot of ions and still have good resolution. And the protocol, which I'll go through quickly, is we just load in some barium chloride. We clean it up so it's only barium chloride. We shine a photodissociation laser to hopefully make some barium ions, and then we just kick it out. And if you happen to drive something, you see like this, where without the laser, you have about 800 ions. And when the laser's on, we see that we lost about 100, but there's a gain of 100 in the barium peak. And Stephen has now sort of got the system down where the error bars are a couple, plus or minus a couple of ions. So we can see things that are sort of apart in 10 to the 3 sort of dissociation. All right, so I'm going to have a little bit of fun for one slide, if that's okay. When Stephen built this device, I actually didn't think it would work, and so I was pretty proud of him. And I said, oh, you should write up an RSI on this, because I think some chemists might find this useful. And he did, and it turns out some chemists are now building these things. But the title of his paper was An Integrated Ion Trap and Time-of-Flight Mass Spectrometer. Well, I didn't think anybody would really notice this paper, but look right here.
Oh, I want to put a sign on it. Sign right there. Danger, sure. What's that? That is an integrated ion trap and time-of-flight mass spectrometer.
Yeah, so they actually came to the lab and took pictures of it, and it actually kind of does look like that. All right, my mom was very proud. All right, so using this thing, we did the only thing we could do, and that was just to try to map out this dissociation cross-section. And that data is shown here. And so once we have that, we went to Svetlana and said, hey, please help us out. She calculated the molecular potentials and said, well, what you've been doing, guys, is driving this guy from the singlet sigma to singlet pi state, which is just repulsive and also dissociates to the ground state. Right? So this was great because it was the first time that we had any real numbers about this molecule. But it's kind of disappointing in some ways because look, we wanted to prove that we can cool this molecule internally. Right? This is like 4,000 wave numbers across. So how are you ever going to use this to get any internal state information? Well, you can see the situation if I throw on the photodissociation cross-section of the individual vibrational levels. And these look just like the vibrational wave functions because of when you do the Frank-Condon integral, the only part that contributes is here. So as you scan the energy, you're effectively just mapping out that wave function. All right? You see, wow, if I can cool this all the way to 0 Kelvin, the cross-section barely changes. Right? And so at first we were pretty pessimistic about doing anything with this. But I guess necessity is the mother of invention, and we thought about it a while and realized, well, you know, if I were dissociating here, because of the node in the v equals 1 wave function, I actually don't dissociate any v equals 1. So maybe I can use that. And the idea we came up with, we've been calling it photodissociation thermometry, and here's a cartoon of it. So this is a zoom in on the bottom of the well, and over here are these cross sections. So imagine I turn my laser here. I dissociate, excuse me, I dissociate all the v equals 0 molecules, right? And then if I turn my mod on, I can hopefully drive population into this state, which I can dissociate. And so this should, having the mod on here should lead to an enhanced photodissociation rate. Now, you know, having a signal of one sign is not always desirable. You'd like to be able to flip the sign to believe it. And it just so happens that over here, the v equals 1 cross section is larger than the v equals 0. So here, if we turn on the mod and drive the population out of this state, we should see a suppression of the photodissociation rate. All right, and so as a function of wavelength, here's what you would see. If you did no cooling, it's just this blue line. If you get 100%, it's the green line. And if you get 90, it's the red line. And the data kind of comes in around 90 to 100%. All right, so I won't talk too much about the value of this, why it's not 100%. That's just because we did stupid things like made our ion cloud too big and our MOT too small, things we now think we know how to fix. But what I'll draw your attention to is this quenching rate. So if you extract from this what this rate had to be, it's something of order Langevin, right? I mean, maybe within a factor of 10 of it. So this idea of, you know, compared to the neutral atoms with neutral molecules where, you know, it took greater than 10 to the 6 collisions for a helium and these helium buffer gas experiments to relax the vibrational degree of freedom. Here we're getting it maybe almost with the unit efficiency, maybe 1 in 5, 1 in 10, right? Right, and why is that? Well, I gave you one hand wavy explanation. I'll give you another now. No one's really calculated anything yet. People are actually working on this, but the way I think about it is that, you know, if you had a 1 over r to the 4 potential, and it was just 1 over r to the 4 all the way down, the collision would cross the origin, right, if you're within the Langevin length. So what that means is you have this really short-range collision, and the calcium is really in there on the same length scales as the molecular bond itself, right? And so it's like you form this trimer, so now any energy here can find its way over here, and when this thing pre-dissociates away, it can take it with it. You can also describe this with sort of a modified Landau-Teller theory, which is more or less just a math way of saying what I just said. But we'll see. Some people are calculating this right now. All right, so let me summarize. Hopefully I convinced you that molecules are worth the trouble and that this motion trap business might be a decent way of approaching this. I don't have a better word from this. There probably is a better word. Told you a little bit about some ion trap thermodynamics. What I didn't talk about is we really just scratched the surface here. We found that there's all kinds of non-equilibrium steady state issues when we really couple all the reservoirs in there, the different ions and the different atoms. We're just starting to understand a little bit of it, but I think honestly there could be a whole other field of research that just comes off of this. That's really rich. And then I told you about our efforts to do 2-stage cooling and the evidence we have for sympathetic cooling of the internal states. And I didn't get to tell you about the second version of the experiment, which we're excited about because we can start working with single ions, and we're going to have these time of flight capabilities so we can really, this chemistry, which I also left out, we'll be able to go back and do a much better job there. All right, thank you guys.
Questions?
So when there's a micromotion heating, does the velocity profile still look like full distribution?
So it actually depends. So if you have a single ion and a buffer gas, you get a power law. And we can actually predict that power law exponent now, which I haven't talked about. If you put more ions in there, then it sometimes looks more Boltzmann, sometimes doesn't. It's just this in-between steady, non-equilibrium steady state problem. And then what's even worse is that I'm sure people like Mikhail know, you also have to worry about your 300 Kelvin background gas in these experiments, right? Especially when you have a lot of ions. And that's a 300 Kelvin reservoir that, okay, it's very weakly coupled, but it's still coupled. And so you can get, Gaussian distribution sitting on a larger one with sort of parallel tails. So there's a lot going on there.
So the long tails, because of how the micromotion makes it like,
Yeah, what it comes down to is the way to think about it is, so if you were to write down a trajectory, you'd write it down as x equals a Matthew cosine plus b Matthew sine, right? Now you think about collisions as taking you on a random walk in the AB space, right? And when you write that down, you see that unlike in the normal buffer gas case where you take a additive random walk, here there's a multiplicative part to that random walk. And that multiplicative noise leads to this power law tail. We actually figured out or found that in finance they work this out when you have multiplicative noise, how do you get power law tails? And we used the result to get it.
So is it basically a Levy flight?
Maybe. We can talk.
I wanted to ask, how do you measure G in your ion trap thermodynamics? And how do you measure the temperature as a function of time?
Okay, so it's very, I would say we estimate the temperature as a function of time. So this graph and all the graphs in this section were log-log graphs. And log-log graphs hide a lot of sins, right? So what we do is we do a very quick scan of our laser over the resonance. And I don't remember the time, but it's quick enough that we barely influence the temperature. We get it from
But so when you look at when you turn the laser cooling off, you show this plot where you have the temperature as a function of time.
Right.
So how do you extract that?
Yeah, from these quick scans.
Oh, okay.
Yeah. I mean, it's an estimate because it definitely messes with it. We also have done things like compare the fluorescence ratio to when it was cool and when it's off, but that's fraught with error as well. So we prefer to say we estimate the temperature.
But can I ask?
Yeah,
so
please.
How do you know that the temperature is the same all over the sample, or just?
Oh no, we don't. I mean, so in most of this stuff, it's hundreds to 1,000 ions, and so it gets closer to thermodynamic. At least in the simulations, it looks that way as well, right? But it's an estimate, and this is a log-log graph. That's the takeaway.
So you showed that your vibrationally inelastic collisions are very efficient.
Yeah.
But other types of collisions like charge exchange can notoriously be inefficient, right?
Right.
So do you always need a level crossing to get it efficient, and does your hand wavy argument address why one could be good and the other one could be silly?
No. So it depends on what's going on with the charge exchange. There can be charge exchange that's very efficient. Like for example, if it's energetically allowed, right, but it requires a non-adiabatic transition, that slows it down. If it's energetically allowed and there's a radiative transition to charge exchange, then that can. I mean, it's sort of a different animal. Is what the answer.
But should you need a level or near level crossing for the vibrational?
No, I don't think. I mean, well, I don't think you have to think about it in that way. Yeah, it's just. I mean, honestly, the way I think about it is it's just this versus that or that. Right. That's it.
Eric, go ahead.
No, I mean, maybe I missed it, but I must have thought of you as just using a string of ions, right? To
All right, we're not very good at ion trapping. Next question. We're headed that way. That's right. Yeah. The ultimate
is that a problem?
No, it's not. No, it's not at all. I know everything would be better. In the beginning, we were really worried about spectroscopy and all that sort of stuff, and we wanted to get to the science quickly. But yeah, okay. We'll get there someday, I hope.
Oh, Eric, so this might be, you can tell me it's irrelevant. Maybe it's one of 10 ways that you said to consider this problem of the ion-ion collisions and so forth. So deep in the solid regime, gamma is 1,000 or something, more than that.
Okay.
My kind of simple picture of what RF heating is when you have relative motion of the ion, it's anharmonic, and therefore there could be parametric coupling to the RF drive itself.
Right.
So therefore, I'd expect the heating rate to maybe go exponential with gamma. I'm not sure that's true, but Is there any connection? I mean,
Well, it's probably a different way of skinning the same cat, so to speak. I mean, we tend to, in this regime, we actually don't even say what it is, because this is just kind of, there's like 4 random points in the solid regime, and it's so low, even from the simulation, we can't extract it. So I bet in the end they're the same. That's what my gut says. But maybe we should talk about it, because it'd be kind of fun to think about it in that way.
pretty small enough.
Yeah, it's tiny. Yes, sir.
A little bit along the same line. I mean, there's been some MD simulations and molecular dynamic simulations through the years, which suggest maybe that the heating rate goes more like temperature to the second power, actually. I mean, just by putting things into a trap, an ideal trap, and then just see how the things.
Right. So, but G is not linear in temperature, I don't think. Gamma is, but G is not. So we should. I have to go back and look at it and see. Yeah. You can make some sort of hand-wavy argument here, which is admittedly probably a dirty lie, that it should go as 1 over G squared by looking at so.
But it's actually in the solid regime.
On the, you mean in the solid regime? Well, so we don't really have enough to say anything about that. But all right, we'll look at it later. Yeah.
Any further questions? Then let's thank
Cool.
everybody.